an object that I can describe very succinctly. Because I have how many inequalities or equalities do I have? N by n matrices? Mr. Ben, how can I represent as a linear program or as kind of a convex set? Okay, so remember when I represented the flow polytope, I wrote some equations over variables, and that gave me kind of an algebraic representation of the set of all passes in a graph. Okay? So what I'm asking now, how can I do the same thing for permutation matrices? Anyone has an idea? Yeah, Joshua?
You can do like the matrix times 1 and like 1.
Very good. So you're describing a set of 2n linear inequalities, which basically is matrix times sum of all rows equals 1, sum of all columns equal 1. That's it. And maybe all entries are non-negative. That's it, right? So there are 2n inequalities I can write here that will represent all such matrices, or the convex hull of all such matrices. This is called the Birkhoff-von Neumann polytope. And you can look it up later. And just like I talked about decisions over passes in a graph, is it working now?
It looks good to me.
Maybe zoom in a bit more, because otherwise they will not be able to see the board. They don't need to see my feet, for example. So I have nice Hoka shoes, but maybe they want to see my face. Is it recording?
Yeah, it's recording.
Okay, good.
It's already recording?
Yep, it's already recording. Yeah, I started upstairs.
Yeah, this is fine. A bit more up, maybe. Yeah. Okay.
Thank you.
Well, this was an example of another structural decision set that I can apply my algorithms to. Question? Between 0 and 1. And what it remains to show, I didn't show, but this is something I'm giving you, this is extra curriculum, okay? I'm not teaching you that, and it's kind of extra material, but I encourage you to check it out. It's written in the book that the Birkhoff-von Neumann polytope, when I write a matrix M, and I have this inequality summation I, M, J, I equal 1, equals summation M, I, J. These set of inequalities, and then Mij greater than equal 0, this is a convex set in R to the n squared, and it's the convex hull of all permutation matrices. So every member of this set, in the interior of this set, can be decomposed into at most poly n permutations. I believe n, actually, exactly n. So this is similar to what I talked about passes in the graph. I'm just giving you another example. Another example for the power of convex optimization. So motivation for today, I'd like to solve an online decision problem with partial information over structural decision sets. For example, passes in graph, that already you know perfectly well, right? I described it in detail, the flow polytope and how to decompose flows into passes and so on. Example number 2, which I just mentioned, but I didn't go into detail, are permutations or orderings of sets. And both of these are very important problems that contain a multitude of possible decisions, exponentially many decisions, and I like to solve them efficiently. Now, not only do I want to have an efficient algorithm, I would like a good regret bound. And on Tuesday, we talked about that in the bandit setting, in the partial information setting, the exponential goes not only into the running time, but also into the regret bound. You recall, Kia, you recall, everyone else recalls that? Very good. So how can I use the power of convex optimization to solve this more complicated problem? I can use EXP3, I can use simple MAB, I talked about it on Tuesday, but they're going to be disaster for this. Everyone understands why it's going to be disaster? No. What don't you understand?
Like, why would?
Okay, who can answer? I need a student to answer this. What's the problem with using simple MAB or XP3? Yeah, please?
I mean, what were you saying? Like, if you have like an exponential thing, then not only does it, like, we already knew the exponential computation, but the regret had like n log n because of 2 the
Yeah, so 2 problems, right? We went through this route in full information, if you remember. We talked about a prediction from expert advice. This was the first class of this first lecture of this class. And we said, okay, this is very beautiful, but it's inadequate to capture complicated decisions. And that motivated online convex optimization and convex modeling and so on. I'm going to do the same now, but for more difficult problems. Problems that we don't have full information. We route a packet in a network, we only see the length of the path. We choose an order of the ads to display, we only see which ad was clicked, if at all. Right? So we have partial information, and I want to model that. Ask me a question if it's not clear. Anyone else? Okay, so the way I'm going to model these complicated problems, and again, I want you to appreciate the complexity of them. I'm trying to learn over a very large set with very limited feedback, and I want to do it efficiently. The model is going to be called bandit convex optimization. And the setting of bandit convex optimization, if I were to spell it out, let me spell it out. It's identical to online convex optimization. The only difference comes in the information, how I get back information. So this works by an iterative game. So for t equals 1, 2, and so on, player chooses xt in some k, which is a subset of R to the n. Then adversary chooses loss function from k to the reals. And then player suffers ftxt and sees only that loss. So there is no further observation or feedback from the environment to the decision maker besides one scalar number. This would be the length of the path if the player routes. She's a router, she's routing packets at the network, she chooses some path, she sees the round trip delay. That's it. She has no idea what's going on in other parts of the graph. Or search engine chooses the placement of ads, they see if there was a click. That's it. They don't see anything else. That's a scalar number. And why is this more difficult than online convex optimization? Jerry, why is this more difficult?
You don't see the gradient.
Exactly. So if I want to apply online gradient descent or online Newton method or any of the other algorithms we looked at, we can't. We don't have the gradient. So that's why this lecture is called Gradient Descent Without a Gradient. But I'm going to show you how to overcome it. It's a very beautiful thing. Questions? Is the setting clear? Is it clear how I can apply it to, for example, online routing? Let's go through it. Who can tell me how can I solve online routing? Suppose I have an algorithm that can be applied to bandit convex optimization. It is efficient, and it has a regret bound which scales sublinearly with time and scales polynomially in the dimension and doesn't depend on the number of exponential points inside of the convex set. Okay, suppose I have that. I haven't shown you how to do it because we don't have a gradient. It's a hard thing to do. But suppose I do. How can I use it to solve online routing? Who can tell me that? Yes, Ben.
Suppose that you're going from home to work.
Yeah.
So you only see how much time that takes for
Right.
the route that you actually took.
Yep.
So I don't know, you can just go from home to work a bunch of times, but take a bunch of different routes.
Yep.
And then use this algorithm to figure out what's the best route.
Okay. So I guess what I'm kind of asking a slightly more precise question, which is, I want to fit it into this framework, right? So I need you to tell me what is K, what is XT, and how does XT tell me which route to choose? And then how do I update how I update that the algorithm does? I didn't tell you that. But these are the two main things.
So K is all the routes that you take to work.
Very good.
And X is the route you take.
Almost. So K is going to be, this is going to be the same as what we did with online convex optimization. Set of all possible routes or set of all distribution of the routes, which is called the flow polytope. Okay. X is going to be a flow. And then what do I do with the flow? Flow decomposition and pick a route from the decomposed flow. Yeah? Yes.
Is that the same thing as sampling a route?
Yes. But sampling according to a very specific distribution that is generated by the algorithm. The algorithm generates a sequence of distributions that are very smart, that can be decomposed into passes, sure, but they have a regret bound. So the expected regret is going to be small, which means that on average, we're going to convert to the best decision in hindsight in terms of cost. Yes?
In terms of making money, it's like celebrating Bayesian optimization and custom.
No, God forbid, no. 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 Okay, Bayesian optimization or anything Bayesian has probabilities in it. There is no probabilities in what I'm discussing, right? It's an adversarial model. Nature can give you adversarial costs. Okay? I'm using the past information in a very particular way in online convex optimization, but it is not a probabilistic, there is no probabilistic interpretation to it that I'm doing some conditional something. I motivated it by optimization theory. Okay? So that's actually a big difference. I do have a friend, Kevin Murphy, he's at Google, and he has a book about probabilistic machine learning. Anyone knows that book? Okay, I wish Devon was here. So we just talked to Kevin. And Kevin is a Bayesian, everything I will say, he thinks of it completely differently in terms of Bayesian mathematics and probability and so on. In my opinion, that's a much weaker viewpoint. I hope you're seeing this, Kevin. Send it to the YouTube. But it's also a beautiful theory, which in my opinion is weaker. But it's beautiful. Also, you can also solve problems this way. Any other questions? Okay, this is conceptual part of the lecture, what I said so far. It's actually more important to me than the mathematical part, which I'm going to do next. I'm going to give you an algorithm and a theorem, prove the theorem, what we do every single lecture. But I want you to understand, it's really important to me that you all understand how this maps into a useful method for a problem that we actually want to solve. It's very important to me. If you are not sure, this is the time to ask. Or actually anytime, ask me anytime during the lecture. But this is the more important higher order bit I want you to understand. And that should be fine even if you don't have a good mathematical preparation. Yeah, Kia?
Why was Ben's answer imprecise? That is, like, why is XT not a path that you would go from point A to point B? Why is it a flow?
So that's a very good question. And the reason is, when we use convex optimization, there is inherently a relaxation in there. The set of all paths is a discrete set. Okay? It's easier for me to answer you when you think of prediction from expert advice. You can choose an expert every iteration. That's a discrete set. You have n actions. The power of convex optimization comes when you say, I'm actually going to consider a continuous set, K, which is a subset of Euclidean space. That will correspond to all distributions over the experts. And that is a nice convex set, because discrete is not convex, right? So to use gradients and define them, to use all the machinery, we must have convexity. Otherwise, none of what I said is valid. Okay, very important point that Kia was making. Yeah? You had a question?
So we choose the point from the distribution that algorithm gives us.
We choose again?
So here XT is what we are choosing, right?
Yeah, but the interpretation, XT is a decision that we use. How do we use it? This depends on the application. So if it's a distribution, and we're allowed to play a distribution, you play from that distribution. If it's a flow, you need to decompose it into paths, because you can't really route a path on a flow. You need to decompose it into a distribution over paths, and then choose a path from that distribution.
So K is the set of paths or K is the set of distributions?
It's a set of paths is discrete. K is a continuous convex set. So what do you think it is? Correct. Okay. Yes.
Just to clarify on Park's question, once you decompose XT into a set of
I can speak a bit louder, yeah?
once you decompose the flow X of t into a set of paths, right? You
Yeah.
choose the path that you will take for iteration t at random from that
Yes,
decomposed set.
yes, exactly right. Exactly right. Because you want the expected cost to be as if you chose from that distribution. If you choose from another distribution, you're not choosing what the algorithm gave you. Okay? This was a good discussion. I hope it makes the conceptual point clear. I'm glad you asked me these questions. Okay, these are important questions. Any other questions here? Let's say I give you an algorithm for online convex optimization, and now I ask you to route packets in the network according to it. You use it as a black box. That's something you should be able to take home and code up and route. I want you to feel that you're able to do that. Okay? More important than prove the theorem, actually, that I'm going to prove. More important. Because that's where the smartness is of choosing the framework. Okay? Very good. So, any ideas on how to design an algorithm for banded convex optimization? Yeah, Jerry?
Well,
Assuming you didn't see this before.
no.
Okay.
I mean, one idea is
Uh-huh.
since we have the tools of OCO, we can try to put it in that framework. I would think that you find a way to like estimate the gradient
Okay.
using like, I'm not sure exactly how, but probably there's some ways to estimate it.
Okay, very good, very good. That's exactly what we're going to do. So I guess the name of the class is revealing. And let me give you the algorithm first, then say it's guaranteed, and then tell you the intuition of why it works or why I designed it that way. So this is called the FKM algorithm. For the name of the authors, Flaxman, Kalai, McMahon. And the way it works is the following. It's for general, for BCO, for banded convex optimization, for the general framework. Then for x1 is going to be some arbitrary. For t equal 1, 2, and so on. I'm going to do the following. I'm going to pick yt to be xt plus delta times v, where v is chosen from the unit sphere uniformly at random. And delta is a small number. Then I'm going to play this yt, which is a random point around xt. I see ft of yt, that's my loss, scalar. And I'm going to define gt to be n over delta times f of yt times this v vector. And then I'm going to update xt plus 1 is going to be projection onto k delta, which I'll define in a minute. Actually, let me just say, define it now. So projection onto k delta of xt minus eta gt. So that's it. That's the algorithm. It looks very, very similar. It's actually equal to online gradient descent, where I replaced the gradient by this vector g, which looks very much like a random vector. It picks a random vector on the sphere and scales it by something having to do with the feedback that I received, and then moves in that direction. Yeah?
What's the difference between the vector V in the place step and the sphere V?
V is chosen uniformly at random from the sphere.
Oh, okay.
So I need to say what V is. Let's call it Vt actually. So this changes from iteration to iteration.
So, thank you.
Okay.
And also, is the learning rate constant?
Yeah, which I didn't specify yet. You can make it time dependent if you want. You can make it iterative. Yes.
What's K delta?
K delta is the set K, which is times 1 minus delta plus delta times 0, or some central point inside the set. So this is called the Minkowski set, and it means I take the set K and move a distance delta from the boundary. This is K delta. Why do I do that? Why do I project onto K delta?
So that YT is in K.
Exactly right. You see, because I move delta, what is yt? I take xt plus delta times some vector. And I don't want it to go outside. This must be a valid point I can play. So the fact that I move away from the boundary means that even if I'm here over the corner, the delta ball is still around, strictly contained inside of K. And delta is some small parameter that I will choose later. Eta is also some small parameter that I will choose later. Yeah?
In the setting, you aren't allowed to play multiple points.
No, not allowed. It's a very challenging thing. I'm allowed to play 1 point. Then the function changes completely. So it's a miracle something can be done here at all. But indeed, something can be done here. So let me give the theorem. This is by Flaxman, Kalai, and McMahon, which says that the regret of this algorithm is bounded by t to the 3/4 for some delta and eta TBD. I'll choose them in a minute after I prove, then I will be able to optimize them as usual. Oh, I should say times n, maybe times GD. That's it. There is no exponential. Yes?
If we don't know the, oh, okay, so like I was gonna say if we don't know the gradients, it is G even, I think, but I guess. Like
We don't need to know them. We don't need to know the gradients, but we need an upper bound on them. Yeah. Yes. Yeah, Joshua?
It seems strange that you choose it uniformly from the sphere.
Oh, absolutely. Everything here seems strange, I would say. Isn't it strange I can even solve this problem? Isn't that strange by itself? I see only one scalar and I'm able to solve it. That's already strange. Changing adversarial functions, nothing to do with each other, and still we can do something. Very, very general setting. But let's see, why? Why is it uniform? Let me give you the intuition. I will prove this theorem completely, okay? Let me first see intuition in 1D. So what is 1D? We have the set K, which is a convex set in one dimension, is an interval. That's what it is, closed interval. I guess could be open as well. But, okay, so let's say -1 to 1. And then what is K delta? Yeah?
-1 minus delta to +1 minus delta.
Very good. So we have like some chop off the corners here, delta corners. So then I start maybe at 0. And then what do? What does it mean to sample something from the sphere? Yeah? Yes. And then what is yt? What does yt correspond to? So sphere means I sample either 1 or -1 with equal probability, correct? And my point yt, if I'm at point x here, then yt is going to be x with probability half. It's going to be negative delta, and probability half is going to be plus delta. That's it. And then I'm going to define g t to be 1 over delta times this f of y. Right? Now let's see what that is. So what is the expectation of gt? With probability half, it's equal to 1 over delta times f of x plus delta. And probability delta is going to be plus half 1 over delta f of x minus delta times negative 1. Which is what? Yeah, but in what? Derivative. Right? Let's look. What is this? This is equal to f of x plus delta minus f of x minus delta divided by 2 delta. So as delta goes to 0, this is the derivative. So even my boy knows that, right? That's the derivative in 1 dimension. Yeah? So this approaches f prime of x when delta goes to 0. That's the intuition. That's why I pick uniformly at random. Yes?
Wouldn't it be better to, instead of sampling from, the shell of the sphere, to sample from the filled-in space of the sphere? Because then the expected value would probably be closer to the gradient if the delta is sampled randomly instead of being on the shell, being in the interior as well.
Well, why do you think it's better? How would it, this you understand, right?
Yeah.
What would it mean in 1 dimension?
Because now the delta, now you're allowed, now the delta can be anywhere from 0 to delta, so then the
Yeah.
expected value would be probably closer to the base too.
It's not clear to me. I mean, you'll have some integral here over all points between minus delta and delta,
Yeah.
multiplied by the value over there, right?
Yeah.
The magnitude. It's not clear to me that this is equal to the derivative.
Well, yeah, no, it's not going to be, but it'll probably be closer than just only sampling delta minus delta.
No, that's what I'm pushing back on. It's not clear to me it's going to be closer. I think it's going to be farther away. But I will say the following. What's the general rule I'm going to use here? So the general rule, so this you're all with me here. You all have seen that, right? This derivative, 1D. Everyone with me on 1D? Okay, let me write down the high dimensional extension. So in n dimensions, this maybe will clarify to you. What's your name?
Ellie.
L. Expectation over V from the sphere f of x plus delta V times V is equal to delta over n expectation of u from the ball f of x plus delta u. So, gradient. What is this rule here that I wrote? Physics. Anthony, who's here from, you're from physics, no?
Yes.
Okay, what is this? Yeah. Oh, very good, Alex. Yeah. So this is called Stokes theorem. You're not a physics student, are you? Okay. So you guys remember Stokes from multivariate calculus? Yeah? If not, it's in your prerequisite. Tough luck. Very good. So this is called Stokes theorem. And the physics, correct me if I'm wrong here. You're the only physics person here, correct me if I'm wrong. The interpretation is that the flux, you can take any shape you want, not necessarily a ball, but you can take a ball. That's, by the way, why I took a surface, not the interior. You take the flux going out from a shape, it's equal to the charge inside the shape. And this is true for any envelope that I pick. Okay?
Stokes is general form of
Gauss.
If it's not Gauss theorem. But
Yeah,
those are
there is
just-
Gauss, Stokes, and Green. And I never understood the differences between them. They're all the same from my perspective. They say
Mathematically,
this.
they're all the same.
Yeah, they say something like that. That's kind of the. I think this one is exactly Stokes, and there are variants of it for more differentials and so on, higher order differentials. Yes.
So in 1D we are approximating f dash x using this f of x plus delta formula, right?
Yeah.
Now, if we, I mean, as he was saying, if we consider a point inside the segment,
Yeah.
then it would be wouldn't it be a better approximation of f dash of x?
That's exactly what I was saying now. No, because I'm using this is the equality I'm using. I don't know how to make that into estimating the. It goes by sampling a sphere and a ball. The flux going out and the integral of the inside. These are the two relationships that are related. I don't know to say that it's, in my opinion, it's not going to be correct if I take inside. It's just not going to be, there's going to be some other approximation. Maybe it's approximately okay, but this is what this is equality here, what I wrote here. It's equality. Yeah?
I think the picture, if you did expectation of V in the ball, then
Yeah.
say, you break it down into many of the spheres, and then each of them is in turn.
I
like a
could do
ball.
that, yeah. I
And
could
then I
do
think that's like biased now or something, because it's biased towards the center maybe.
It might still be close if delta is small, so I'm not going to rule it out.
Yeah.
But if you want to come up with more complicated objects, I'm sure you can. I'm sure you can overcomplicate it more. This is the simplest, most elegant form of it that I know. I can say the following. There is one more, maybe even simpler thing you can do. Suppose I take some standard basis vectors, and I pick one at random, and in each one of them, I do this 1D estimation. That would also work. See what I'm saying? So I could have done that too. That would be a discrete set I'm choosing for. I think this is nicer. That's my feeling. It's a bit nicer. But I could have done the other estimation, which I think is equally simple. The interior, I don't know how to prove that it works. This I know how to prove. I think the interior will also work, by the way, but with maybe not as nice bounds. Yes?
Can we try to make this algorithm better, but like somehow reducing variance of the expectation? So basically maybe like saving previous observations, so basically have functions, maybe saving somehow
Yeah.
previous values.
Oh, very good point.
And maybe by using this we can decrease variance, because expectation is basically exact,
Yeah.
but maybe varies.
Yeah. Your name again?
Bogdan. Bogdan.
Bogdan. Okay. Russian. Okay. So the it's Russian, no?
Ukraine.
Ukraine. Okay. Sorry. sorry. Once I got cursed, I asked someone if she's Russian. That I got cursed back at me. Remember that in the seminar? Okay. My apologies. So, where was I? Yeah, the question Bogdan had is about variance. So, and the reason I guess you're asking is because the regret bound here, t to the 3/4, is not tight, or at least doesn't appear to be tight. We don't know. Maybe it's tight, maybe it's not. Clearly, it has to be above square root t times n. That we know, because we've seen that's tight for multi-arm bandit. It has to be bigger. This is a more general problem. However, maybe it can be improved. Indeed, it can be improved. And I will get back to it at the end of class if we have time. But this requires much more sophisticated tools, much more sophisticated. So this is a very elegant, very simple algorithm. Not easy. Again, don't misinterpret me. I'm not saying it's easy. Nothing I'm teaching you is easy. But it's elegant. It's beautiful. It's simple. I'm allowed to be happy about the beauty of it, right? I think that's legit for me to be. But it's not, I'm not saying it's easy, but the extension to tighter bounds is difficult. It's very difficult. If we have time, we'll go into it. I think I'm not going to go that because I can spend 2-3 lectures more on this topic alone. And I want to reach many more interesting things. Game, linear programming, dynamical systems, a lot of things. Okay, more questions? Yes?
This is kind of going back to the beginning, but how can we convert a doubly stochastic matrix into a permutation matrix? Because the constraints are just like, oh, the rows and columns sum to 1. Like it's not necessarily like 0, 0, 1, 0.
That's right. So what I was saying is that a doubly stochastic matrix is the set of all distributions that represents a distribution over permutation matrix. Every permutation is a double stochastic matrix, clearly. It sums up to 1 here and here. And the converse says that if I have a double stochastic matrix, I can decompose it into n permutation matrices. This is by Birkhoff von Neumann decomposition, and I didn't prove that, but it's a great exercise for you to think about. It's very analogous to flows and paths. Yeah? Any other questions? All right, so I think I'm ready to prove. So I'm going to need Stokes' theorem, which I'm not going to prove because it's all in your prerequisites, but that I wrote over there. So I need that the following is true. So n over delta, expectation, f of x plus delta v. V is from sphere times v is equal to the gradient of the expectation u in ball f of x plus delta u. And this I'm going to define as gradient of f delta hat at x. So what is f delta hat at x? This is the average function. If I take f and I average it in delta ball, intuitively it's close to f because I do like local averaging. So this is just the expectation of f of x plus delta u. U is in ball. So the way to think about it, if I have a function like this, and I take a small ball here, f hat is going to be the average. It's going to be here somewhere, right? That's going to be the value. It's a very, very close function to f. So it's not equality. If delta goes to 0, it's exactly f. That's the one-dimensional gradient inequality I wrote. Otherwise, it's a gradient. So I will need that. Then I will need, this is 1, 2. Let's see. So I need the following fact. For every x in k, there is a y in k delta such that f of x minus f of y is less than delta g, just delta g. And why is that? Yeah, Lipschitz, right? Gradient bound. So in your homework exercises, you were able to, if a function is Lipschitz, this is always true that it's less than g times x minus y. It's Lipschitz inequality that follows from gradient bound, and that's bounded by delta. Why is it bounded by delta? Yeah, they're close. That's how I define k delta. It's just delta close to k. I just shrink it by a little bit, by delta. Let's see, do I need anything else? Yes?
Wait, sorry, I'm not 100% sure, but is it possibly 2 delta? Because at the very furthest, you're shrinking by delta and then you're moving in a direction by delta. So if the gradient...
I think it's delta, but even if it's 2, where you will forgive me for a factor 2 here, but I think it's just 1 delta.
Is the whole
Because
thing
I project, so take the set k and I project onto a point in k delta and it's delta close to it. I believe that's correct. But please check me. There could be a factor. I don't see why, but there could be. You're saying why would it be?
I'm just thinking that the greatest distance between 2 points in k and k delta is 2 delta, right? Not delta. But there might be other points that are delta apart.
I mean, Lipschitz inequality is, so convexity implies, how is this proved, right?
Yeah.
We use convexity, so gradient f at x, y minus x. And then we do Cauchy-Schwarz, right? There's a g times the distance. There is no 2 here.
I just mean that k delta and delta, like the y minus x I thought was 2 delta at most, and not delta.
Oh,
because you shrink by one minus delta.
By
and then
factor.
you shift by factor 1 minus delta,
Oh,
and then you shift.
There is no. Assume that 0 is the centroid of the set. Yeah, I can do that actually without loss of generality. I can shift everything towards the origin.
Yeah.
Otherwise, it gets confusing. So I think you might have a point here. Let's take it to be delta. Yeah.
So in the original algorithm, like x is in k delta, but then here, y is in k delta.
You want me to replace x and y?
It's just like naming things, right?
You will forgive me for that. Okay, thank you. I think variables can be replaced. I mean, you're saying that yeah, okay, fine. You're right. No, actually, I always use y and k delta. That's how I will do that. Oh, you're right. You're right. Okay, I will replace. You're absolutely right. But I only need to replace it here, right? So, okay. Good. Any other concerns about notation or anything? I believe that's all I need. I'm going to assume, I will assume that f of x, ft of x is bounded by 1 for all x and k and all t. I'm going to assume a bound. If it's not 1, that will go into the regret bound as well, just as we always do. And now let's prove the theorem. So let's look at the regret. Of the FKM algorithm, which is summation ftyt minus ft of x star. So first thing I'm going to do is convert this to the regret of xt. I don't like the yt here, that's a random point. So I'm going to convert it ftxt minus ftx star plus delta gt. And why is that? Yes, exactly, property 2. So the two sets are, it's not even that. I mean, the 2 points are close. I don't even need property 2. I just move delta. So yt and xt are delta close to each other. Okay. Second thing I'm going to do is, unlike x star here, it can be on the boundary of x, of the entire k. And I always shrink to k delta. So I want to convert this x star to something that I call x star delta plus 2 delta tg. And here I'm going to use fact number 2 over there. Okay, so x star delta is the optimum inside of k delta. So I'm only comparing myself to points that I actually play. I'm not allowed to play on the boundary, right? I always move. I need some kind of wiggle room. If I don't have wiggle room, I cannot do the randomization. So I cannot compare myself to something which is outside of my wiggle. That's unfair. So that's why I shrink the set, and I only compare myself to things inside of the set k delta. Good. Okay, yeah. Well, what I'm saying here is that they're actually not that different. That's what I'm saying. So for every x and y, you can shrink them and they're close. Okay? Yes?
So is x delta star the best you can do in k delta, or
Yeah.
the projection of the?
It doesn't matter, actually. It doesn't matter. So let me call that the argument over x in k delta summation t ftx. So the argument inside. But for example, this could be obtained by just taking the closest point, and this is only smaller. Okay, so I guess no. I will take the projection. Let me take the projection. So x star minus x. So this way, okay? I'm using fact 2 without confusing you guys. Good. So now I would like to convert this. I'm using ft. And I don't have the gradients for ft. But I do have the gradients for f hat delta. For these I have the gradients, right? So I want to convert this to f hat delta. And my claim is this is less than summation t f hat delta xt minus f hat delta t xt x delta star plus 4 gt delta. One from here and one from here. So why is this true?
Sorry, what's the subscript there in the last formula?
Here?
Like, no, before, after
This?
F, yeah.
This is xt delta. Xt delta. So I have ft, and similar, you saw here how I defined f delta hat to be the average around the small ball. So I do that for ft, and I call that ft delta. Is it clear? Yeah? Is it clear, folks? Yeah? Yeah? Joshua?
Is it because of like convexity of that or something like that? So on average and something.
I don't need convexity for that, actually. I don't need this will be true even if f is not convex. Jerry?
Is this just Lipschitz cut over that?
And voila, good. So Lipschitz, I'm averaging over a ball. Okay, so in a ball, I cannot move more than delta away. The function is Lipschitz, cannot change by more than delta. So therefore, f delta hat and f are close. Surely? Okay? Good. Yeah? Do I need to prove that, or you guys are fine with it? I need to prove? No. Okay. That's the answer I like to hear. No. Yeah? Good? So this is just, my claim is that, you see, my claim is that I'm using here that f delta hat at any point x minus f of x is less than delta g. That's what I'm using here. You agree that this is true? It's just by definition, it's averaging, yeah? You guys are fine with it? Good. Okay, so this is just justification. Good. Now I go to a place where I wanted to be. What's written here? What is this? Yes. Exactly. So what I have here are functions that are applied online, and I know their gradients. And how do I get xt plus 1 from xt? By gradient descent over these functions. That's exactly what I'm doing. So this term here is the regret of OGD over the f hat t deltas. That's what it is. You agree? That's exactly what it is. That's what we analyzed in lecture number 3. Plus 4gt delta, let's not forget. And how did we bound this regret? We bounded by eta times the sum of the gradient norms, dt, plus d over eta, plus delta for gt, norm squared. This is theorem I proved to you in lecture number 3. You all remember, I know. I'm sure you do, right? Good. Now, how big are these gradients? What's the magnitude of them?
G.
G is the gradient that I'm using. What am I using? Where's the algorithm? Did I delete it? Oh, unfortunately I did. Remember how I defined the algorithm? I defined G in there, and that was equal to n over delta times the value of f at x plus delta u, v, times v. Remember that?
Right.
Do I need to write it again? Let me write it again. So remember G. Remember, gt is equal to f of xt plus delta v times V times N over delta. That's what it was. That's what I used in the algorithm. Why no? Yes, that's what I had. Okay. Yeah? Good. So what is the bound on how big is GT? Exactly. And N squared over delta squared. I think I can use the beautiful clean board. So this is at most eta times N squared over delta squared times T plus, I believe this is D squared actually. Squared. D squared over eta plus delta T GB. And if you tune eta and delta correctly, you will get that this is O of NGD T to the 3/4. I believe eta here needs to be 1 over 2 to the 1/4. And delta, and so on. You can compute what it is. I can write it for you. So then eta needs to be, okay, I'll just leave it at that. So this is what it needs to be. Yeah.
What about the value of f in GT?
I assume it's bounded by 1. You see? It's over here. You see over there? Okay. Very good. Yes.
I know this doesn't really matter, but I think there is also a factor of 1.
Oh, even better than what I wrote.
I guess for the first two.
Okay, but this inequality is still correct.
Yeah, this is still.
Yes, Angelos?
So we have so this is not all tight, right?
It's not tight.
Do you have tight lower bounds and upper bounds for the set?
Okay, so lower bound, this is a harder problem than prediction from expert advice, and it's a harder problem for multi-arm bandit. Okay, good question. So to answer Angelov's question, because BCO is more general than multi-arm bandit that we had on Tuesday. So this implies that the regret has to scale at least root Tn. Then Bogdan asked me, how can we get better bounds? And indeed, this has been a subject of a long line of investigation. So what happens is, when we have a convex set, and we choose a ball here, the ball is not the optimal shape. I think you're pointing out it is not the optimal shape, because maybe we know that the function is more concentrated in some area, less concentrated in another area. A. B, maybe I want a bigger set, because if I kind of restrict myself to delta radius, I suffer the 1 over delta. And there is something called, which I'm just going to kind of tell you in words, but not prove. There is something called self-concordant barrier functions. There is a function that fits the set, and that will give you some kind of ellipsoid here. And with a lot of extra machinery, it's possible to get something like n squared or even n root t if the ft's are linear. This is a very nice algorithm. It's in the book. The linear case is what we were using for permutations, what we're using for one on shortest path. Now you can ask what happens for general convex functions. Again, long line of work, Stroner convex, non-Stroner convex, and so on. This has been, I would say, resolved by Tor Latimore very recently, and he gets root t poly n in general by a very elegant algorithm. But sophisticated machinery. Some form of Euler-Newton method and more techniques. And he has a book on this subject, a whole book, just on BCO, that actually I encourage you to look at. It's a very beautiful book. And he's at Google DeepMind London. Good. Any other questions? So I guess maybe a bit of discussion, which means I can sit down. So, any other questions? I think I'm not going to prove anything else for now. Yes?
Generally, currently we assume like gradient upper bounds of like the capital G that we assume.
Yeah.
Are there like more, and this is a very general setting that is good, but can we like define a class of hardness of our loss functions that can do better?
Oh, so the question is, are there certain types of loss functions for which we can have better bounds?
And is there like a classification that this loss function is from this particular class?
So you remember that for, I guess you're asking because for online convex optimization, we had logarithmic regret, which was much better. And for strongly convex losses, for X-concave losses, I spent 2 classes talking about these better bounds. This is not possible for general bandit optimization. Even for quadratic losses, you must suffer at least square root n. So it's possible to prove that. And the reason is that you can have, just the bandit information doesn't allow you enough to extract the curvature. There are some special cases where you can get logarithmic regret, but they are much more restricted. Yes, Alex.
So I just wanted to clarify, so the bandit convex optimization is like, I guess, more useful over the multi-arm bandit when you have like a large space of like actions, but that large space could be represented by like a lower dimensional like probability distribution over those actions. Is that what you're talking about?
That's a very good characterization. What you said is a very good characterization. So Alex was saying, when is this bandit convex optimization useful? And you were saying one place where it's useful when we have a very large action set that we can describe by a distribution over a smaller low-dimensional set.
Yeah.
I would say more generally, every time you have convex modeling, where you can use the power of convex optimization, which is a very general, in every branch of science, we're using convex optimization to model what we're trying to study, what we're trying to optimize, what we're trying to find. Search or feasibility or decision or whatever your objective is, the language of convex optimization is very general. It allows you to talk about these things in an efficient way. So every time you have a convex set in Euclidean space and convex functions apply to them, this is a better choice than multi-arm bandit. And yet, discrete is also very general. If you have 5 algorithms and you don't know which one to choose, multi-arm bandit is usually enough. So you can apply multi-arm bandit to 5 algorithms and choose the best one between them on the fly. Good. More questions? Yeah?
When you define your delta G up there, there's like G x minus y for your delta, but it says for all f x y minus.
You're going to force me to stand up? Okay.
Sorry.
Again? Yeah?
When you define your delta G, G times x minus y, that like distance between them, is that for all f x y minus v or y minus x?
Second point? You're asking about the second point? No, I'm saying for every y, there is an x that is close to it. For every y out in k, there is an x in k delta that's close to it, delta close to it. That's all I'm saying. Okay? Not for every x in the world, because x, it could be very far away. Then, of course, there is no close point. Yes, Jerry?
So for this algorithm, it seems to me that all the power invested flows only to the OGD, and everything else was just using Lipschitz stuff. Is there?
Kind of. I mean, I don't think it's a fair characterization, because even without the algorithm, there is power to the modeling itself, just by thinking about it in a convex way. That you think of distributions as points in a convex set, and you can talk about flow decomposition or Birkhoff von Neumann decomposition. That's a very powerful paradigm.
Yeah.
So it's true. Now you have it. You can use Roland gradient descent. You can use Newton method. You can use whatever method you want. But the main conceptual point, I was trying to make that in the beginning of lecture. I want you to think conceptually what it means, because that is a very powerful. If you get that from my class, I'll be very happy. If you're all able to apply that to whatever problem you later on encounter, that's a very powerful paradigm to use. And you will be hard-pressed to find where it is not used. I'll be kind of suspicious. If you tell me I have an algorithm, it's not convex optimization. I'll be very suspicious of you. It's possible, but I didn't find so many such examples. Yeah.
I think I'm curious, I think we use convexity in describing the key value case. Otherwise, you could construct pathological examples where you can redefine that.
Oh, the convex set. Yeah, convex set is used all over the place. Is that what you're saying? Yeah.
Yeah, like
Yeah.
what convexity is.
Yeah, the Minkowski set, so that's true. I mean, that's the set of convexity is very important. The fact you're able to do projections efficiently. There are many things here that are,
I guess my question is like the convexity of the function itself.
yes,
Is there
that's,
more we can squeeze out?
yes, that's true. And in fact, there are notions of non-convex regret, which have been rediscovered, but they go back about a decade. And you can talk about what happens when set K is convex, but the function is not convex. That's the case in deep learning, for example. You have constraints over the weights, but the function itself is not convex. And they can talk about trying to get some gradient equal to 0, or you have an oracle that's able to optimize. There are various kind of modeling decisions you can make and talk about them because of the robustness of the technique. Yeah.
Could you elaborate a bit more on the difference between BCO and MAB? Like, what are the cases covered by BCO which aren't covered by MAB?
Well, passes in a graph, for example. They are covered by, MAB covers everything, just not efficiently. You will have exponentially many passes in a graph. So if you treat each one as discrete, you will have too many. Permutations, that's what I started off the lecture today with, right? So permutations over a discrete set and so on. Very good. I think we'll stop for today. We'll continue Tuesday. If there are any more questions, I'm still around here. Talk to me.